Okay, let's take one last look at a little more complex problem here. This problem involves three parts of this system. So in order to do this, we've got to break it apart into its pieces, create a free body diagram for each piece, and then put it all back together. So in this case of connected objects, two objects are connected by a light string. Normally we use the term light string when we want the string or the cable or whatever like that to be insignificant. It has no bearing on the problem. Okay, so it's not going to add anything or take anything away. The string passes over a frictionless pulley. That's another key right there. Frictionless means that it doesn't add or take away from the calculations or the problem. The coefficient of sliding friction between the 4 kg object, the 4 kilogram object, that's the box on top of the surface here, and the surface is 3. Find the acceleration of the two objects and the tension in the string. So as the 7 kg weight is dropping, it's pulling along the box across the surface. So we've got some friction on the surface. So the reasoning here is that connected objects are handled by applying Newton's second law separately to each. The free body diagrams for the block on the table and for the hanging ball are shown. We let's make that, can I correct it? Yes, there we go. We shall obtain two equations involving the unknown tensions, and that can be solved simultaneously. God, I can't believe that. Okay, so we've got our free body diagram for the box. We've got the normal players in here, the normal, the weight, the tension, and the friction. And for the free hanging ball, we've got the tension and the weight bearing down. So to look at this, we start taking it apart. Let's start with the box on the table. With the positive x direction to the right and the positive y direction upward, Newton's second law applied to the 4 kilogram object gives for the first free body diagram. So what we're going to do is we're going to look in the x direction. So the friction and the tension. So summing the forces in the x direction, we have the tension in the cable leading to the pulley minus the friction, which is between the surface and the box. Since the box is going to be moving, we are going to let that equal mass times acceleration. And the mass, m1 here, is actually of the box. So now if we start inserting what we know in our givens, again, the summation here of all the x forces, tension minus friction, is equal to 4 kilograms times acceleration. So we're not getting a lot of solutions here, but we are getting a good setup. So what we need to do is, since we can't go any farther with that, we need to switch to the other axis. So let's move to the y-axis. The function of the forces in the y direction, the summation, is the normal force minus the mass of the box times g, and since there is no movement in the y direction, we set that equal to 0, or the equilibrium. So the summation then of the forces, then again we start putting in the known values. We've got a normal, unknown. We know that we've got a 4 kilogram box. We know that. Gravity, and we set that equal to 0 because it's in equilibrium. So now, because the friction on the left is equal to mu kn, which is equal to mu k, n is equivalent to the weight, m1g, you can see that from the diagram, straight up, straight down, we have 3/10 times 4 kilograms times 9.8 meters per second when we put each of our terms into the relationship. So now we have a coefficient of kinetic friction equal to 3/10 of 39.2 kilogram meters per second squared, which gives us 11.8 newtons. So we can use those two terms back and forth. We can call it newtons, and it makes it easier instead of constantly calling out the kilogram meters per second squared. But always remember that you can decompose newtons back to its fundamental terms. Therefore, the tension in the cable off of the right side of the free body diagram is equal to the friction coefficient of kinetic movement is equal to 4 kilograms times the acceleration, which is equal to 11.8 newtons plus 4 kilograms times the acceleration. Okay, so we're drawing on the terms, each one of the components in the relationship here, so that we can take all of the x terms now, plug in the values, and we've gotten just a little farther. So now we've gone as far as we can with the box. Let's switch to the free hanging weight. Now we apply Newton's second law to the 7 kilogram object moving in the vertical direction, this time selecting downward as the positive direction for the second free body diagram. So in this one, we have purely y direction. So if we sum the forces in the y direction, we have the mass of the sphere times gravity minus the tension in the light string, and again, it's moving. It's not in equilibrium. Mass 2, which is the 7 kilogram sphere, times the acceleration. How many of the known values can we put in here and see if we get any farther? Well, we have mass 2, we have gravity, we subtract it from the tension, and that's equal to mass 2, 7 kilograms, times the acceleration. So now what we're going to do is we're going to move the terms around, solving for the tension in the cable, okay, the positive tension in the cable. So we pull down our terms, 7 kilograms, this time insert 9.8 meters per second squared. We're going to subtract from the other side of the equation, the right side, our minus 7 kilograms times the acceleration. And what we end up with when we start combining our terms and doing our operations, 68.6 newtons minus 7 kilograms times the acceleration. We still don't have an acceleration term. So 6.68 newtons minus the 7 kilograms times the acceleration now is equal to the 11.8 newtons plus 4 kilograms times the acceleration from our previous problem. Okay, so go back here. There's the relationship where we summed in the x-axis. Okay, so solving. So let's pull all the values together. 68.6 minus 11.8 gives us 56.8, and that equals 11 kilograms times the acceleration. Okay, so what we did was we factored the acceleration out, these two values, and subtracted them from the other side. Now, acceleration is equal to 56.8 newtons divided by that 11 kilograms. We have kilograms here, we have kilograms there, so what we're left with is purely acceleration, 5.16 meters per second squared of acceleration. Okay, that is the acceleration on the x-axis light string, the acceleration on the y-axis light string. So now substituting the acceleration into our relationship, tension is equal to 11.8 newtons plus 4 kilograms times the acceleration. Now everything has a numerical value. The tension then is equal to 11.8 newtons plus 20.65 newtons, or 32.4 newtons. So we were able to solve for, knowing the acceleration common across the string here, we were able to solve for all of our unknowns in the relationship. So that finishes chapter 4 and frictions, and a fairly complex problem. When we come back, chapter 5, we're going to look at work and energy and look to see what potential energy can be used and kinetic energy can be used to help us solve the problems a little more elegantly than we've seen before. Conservation of forces and conservation of energy, and finally, power.